today that we will wind up the this activity. So any doubt, then please check out. The, most of the this material that we have uploaded in the past, the, some of the material that we have not uploaded, so we will upload soon this weekend. Get all the material that's taken by the expert, PDF and this PPT and this and from session of this Python code. So get everything, each and everything material from this website. Okay. So now today that we will start our say the last topic of this unsupervised machine learning, that is the clustering technique. So now this one is the Gaussian mixture model. Gaussian mixture model. So this Gaussian mixture model is the clustering technique. The clustering technique. We call it as a Gaussian model-based clustering technique. Gaussian name that is coming here in the title itself. So the Gaussian model-based clustering technique. So in unsupervised machine learning, okay, so there is the clustering. So here that thing that we had discussed, the K means we had discussed the hierarchical clustering. Third, that we had discussed DB scan. Fourth one, that is our today that GNU, that is a portion. So this algorithm that is based on the normal Gaussian distribution. The benefit of this GMM is it provides the soft clustering. GMM provides the soft clustering. The GMM actually is similar to this K-mean. K-mean and GMM that almost similar, that we'll see in detail. But this GMM, the advantage of this GMM is it provides the soft clustering, whereas the K-mean it provides the hard clustering. Hard clustering. So hard clustering means we put a data point in either of the clusters. Okay. It is a data point in either of the cluster. So one data point or single data point cannot be a part of more than one cluster. One data point or single data point cannot be a part of more than one cluster. Okay, that is a hard cluster. This one is a hard cluster. But as per this GMM algorithm, GMM is the soft clustering technique. So one data point, single data point, can be a part of multiple clusters. Part of multiple. There is multiple cluster. How it can be the part of multiple cluster? That is on the basis of the probability. On the that we will see in detail. That is probability. So this is one difference in between the K-means and GMM. The GMM and other clustering technique. Because here this GMM, the advantage is there are so many other advantages that I will discuss. So that is it provides the soft clustering. Right. The second advantage of this GMM point is this GMM it provides the density estimate. Also provides the density estimate. So this algorithm not only do the clustering but also provide which distribution provide distribution the data point flow. Okay. Is which kind of distribution the data point that follow also provides this type of information. So this data point that follow the normal distribution. Okay. So like so it provides the density estimation. In detail, does it mean density estimation? But for the time being, just to understand, if it not only gives us the clustering technique, but also provides the density estimation. So now density estimation. If you this understood this density estimation, yes. If we have the density estimation, means if a point means which distribution the data point follow is let's say if the data point follow the normal distribution if we know the normal distribution that is in normal distribution there are two parameters that is mu and sigma. So if we know this mu and sigma that we can generate more number of data points. Okay. So that we have the extra information about the data. So we know the distribution, okay, we know the distribution, we know the mu and sigma, so we can generate the new data point. So it's a generative model. The ChatGPT, but it's a generative model. Hope you understand a little bit about this density estimation. Okay, so this density estimation that we see in more detail when we discuss the core intuition of this game. Now, this GMN, GMN, that we can define this GMN in a one line Gaussian mixture model. We can define this. It's a you can say it's a brother of K means. It's a brother of K means. It's K means algorithm from from different planet. You can say from another planet. Okay. So if you know the K means, we understand the DNA. The K means you can easily understand this DNA, the Gaussian mixture. This the difference between this K means and GMM. This K means is based on the distance centroid. Yes or no? This K means that is based on the distance and centroid, where this GMM that is based on the probability and in terms of the parameter of the Gaussian distribution. So this GMM that depends on the probability and parameter of Gaussian distribution, normal Gaussian distribution. Yes, that is sigma that you will see mu and sigma. Okay. So now there is a relation between this kind of small relation between the GMM and K. Okay, so let us understand this GMM. So now let us say that I have a data set, let's say one-dimensional data set, one D data set. So one D data set, let's say we have the height of a 5%, height of 5%. So that is a one-dimensional data. So height, that is a 4.2 feet, 3.9 feet, 4.1 feet, 5.8 feet, 6.0. Clear? So based on this one-dimensional data, I want to do the cluster. Okay. So out of this sign, some of the points that make the one cluster, and some of the points that make the another cluster. Okay. So this one-dimensional data, so this one is a one-dimensional data. So this 4.2, this is a 4.2, so this is a 3.9, 4.1, okay, this 5.8, 6.0. Okay. So this is the data set of the children age. This one is the data set of the children age. Okay. So now we can easily, there will be a two cluster. So the one cluster is this one, another cluster. Okay. But the question is how GMM that will do this cluster. So our with the naked eyes, so we can easily identify, we can easily say there are two type of cluster, means two cluster. This one is a cluster one, this one is a cluster. How this GMM can do this? Okay. So first point is, first we have to check. Okay. First the model that will check. The model that will check this data is composed of many combination of Gaussian distribution. Correct. Point is this data set is composed of how many combination mixture, how many combination of Gaussian distribution. So is this data is made up of mixture of 5 Gaussian distribution? Is this data set composed of combination of 2 Gaussian distribution? Is this data set combination of 3 Gaussian distribution? So first the model will check the answer of this question. How many combination of Gaussian distribution this data is made up of? Okay. So now as per this one-dimensional data, so this data is generated. This data is generated by the combination of 2 Gaussian distribution. By the combination of 2 Gaussian distribution. Okay. So here the K value is equal to because we can see by naked eye that k is equal to 2. Okay, so the model that will pick a Gaussian distribution randomly. Model it up for 5%. So now the model that will pick the two random Gaussian distribution. Okay, so maybe two Gaussian distribution. Yeah. So that is the reason to call this algorithm Gaussian mixture. So here for this distribution, Gaussian distribution, we need only the two things. Okay. We need only the two things to plot this Gaussian distribution. First one is the mean, another one is sigma. Okay, that is standard deviation. Okay. So initially that we don't know the value of this mu and sigma. Don't know from where it comes. So this random value of this mu1, mu2, and sigma1 and sigma. Okay. So we don't know from where it comes, but only the information that we have, that is k is equal to 2. So randomly that we draw the two Gaussian distributions. Okay. So here we are not calculating the centroid. Here we are finding the line distribution of the data. K means we actually always give prior information or prior number of clusters in advance. We have to give the number of cluster to algorithm prior. Okay. And assume any random centroid. Correct. So that is the similarity in between this k means and k. Here in the k means, okay, so let's say these are the data point, Okay. So here the k value in advance, k value that is equal to 2. Okay. So this one is a 1, k is equal to 2. Okay. So now k is equal to 2 means centroid. So this one is a 1 centroid, this one is another random. So we pick this centroid around this data set. Correct? Any 2 point as a sample. Then calculate the distance from this data point to this centroid and distance from this data point to this centroid. And whichever is less, the data point belong to that centroid. Then again we calculate the centroid and we will do the same procedure again and again. Now this is the k. Now is that clear? So this distance is less. So now one cluster. Okay. This one is the one. That is the centroid. The C2 and centroid of this one, that is the C1. Now again, just calculate the distance from this data point to this centroid and this distance from this data point to this. Again, just check the distance, whichever is less, the data point belong to the cluster. Okay, that particular cluster. So now again, that is this one is the updated C1 dash. So now again, just we have to find the recalculate the centroid. Okay. So another the new centroid, again just check the distance from the data point to the updated centroid is C1 double dash and C2. Whichever is less, the data point that belong to that particular less distance of centroid. Now is that clear? This K means is clear? Of this K mean that is clear? Okay, fine. Now here in the GMM that we assume this one this Gaussian distribution. Okay, random. We don't know the value of this mu and sigma. Okay, so here the in K means the updated this centroid that is based on the distance. Okay, means whichever the distance is less, so the data point that belong to the lesser value of the distance of the cluster. Okay, so this updation of this centroid is based on the distance, that is based on the distance. But here this Gaussian distribution curve. Okay, so the new this updated this curve. Okay, this one. So this one is based on the likelihood. So based on the likelihood. Okay, based on the this PDF, probability density function, this PDF. Clear? So now see, this one is my this blue data point, and this one is my red data point. Clear? And here, sorry. Okay, so now this one, this distance and this distance, not distance, this likelihood. So this one is the likelihood. Okay, so this is the likelihood to become the this is the likelihood of a data point to become blue, and this one is the likelihood of a data point to become red. Okay, so here the density of the data point to become blue is more. So this one is the data point, that is a blue data point. Okay, so density of a data point, this data point, let's say this one is a first data point, second data point, and third data point. So first data point, so the density of a data point to become blue, okay, is more, and density of this same data set to become red is less. And here the density of this, let's say fourth and fifth, the density of this data point to become red is more, and density of this data point to become blue is less. Okay, so now the centroid. Okay, now again, not centroid, sorry. Now again we have to recalculate the this likelihood, not centroid. In the K means that we recalculate the centroid on the basis of the distance, but here we will recalculate the likelihood. Okay, so now this one, now these data set, this 1, 2, 3, so these data set, these data points are perfectly 90% to be a blue Gaussian distribution. Okay, so now earlier, let's say this one is a 75% blue and 25% red of these three data point. Okay, so now after this recalculate this or this shifting of this Gaussian curve on the basis of the likelihood. So now this time the data point are 90% to be blue, okay, and 10% to be red. Here that is 90% to be red, is this one is the kind of the probability, and 10% to be blue. Clear? So now we know not only the cluster but also the Gaussian distribution also we know. So from this mu1 sigma 1 and mu2 sigma 2, we can generate the more data point if we want. So we can generate the more data point. Okay, so that is a data augmentation. If suppose small data set that we have, we can generate the more data point more accurately in this GML. Okay, so now you can ask the question how to calculate the likelihood. How to calculate the likelihood? Okay, how do we know the point is X% blue and Y% red? How do we know? Okay, so question is how to calculate the likelihood, because on the basis of the likelihood that we will shift this Gaussian curve, okay, towards to left or right. So based on this likelihood, okay, then next one is how do we know the point data point are X% of this, let's say blue, and Y% is that red. Okay, and the last one, what amount of movement, this one, what amount of movement we need to shift the distribution. So now question is how did you draw these two curves? Okay, yes, I will tell you this curve. So initial, so at very first step, so we don't know this mu and sigma, mu1 sigma 1 or mu2 sigma 2, we don't know. First we initially random just plot this Gaussian distribution curve. Like here in the K means that uh, 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 the two this centroid initially that we pick as a data point as a centroid, randomly. Then according to the based on the distance, okay, then we check which one is minimum, then the data point belong to this closest distance of the centroid. Again then recalculate the centroid, okay, and then again we do the same step repeatedly. So here the same point is we don't know this mu and sigma, okay, so we will just draw a Gaussian distribution random, okay, at random, and then the moment of this shifting of this distribution, that is based on the likelihood, that is based on the this probability density function PDF. Okay, so Now this one is a one dimensional. Now the same that we can do in the two dimensional data set. So now in two dimensional data set, that is multivariate normal distribution in place of the normal Gaussian distribution. So that is a multivariate normal distribution. So multivariate normal distribution. Can anybody know this multivariate normal distribution? So this this normal distribution means it's a normal distribution in higher dimension. It's a normal distribution in higher dimension that we call as a multivariate normal distribution. Single dimension, that is a normal Gaussian distribution. Okay, so normal distribution that we have, say, random variable that is x, and this it is represented by this Gaussian distribution that is n, mu, and sigma. Okay, and the formula of this one is sigma, this root of 2 pi e exponential of minus 1 by 2 x minus mu divided by sigma and 4 square. Okay, so this is the representation of a normal distribution of one input column, that is the only single this random variable, this x. If more than one input, let's say this x and y, okay, or that is x1 and x2, if more than one input, then we will call as a multivariate normal distribution. Okay, so let's say this x1 is a marks in the 10th standard, and x2 that is marks in the 12th standard, and y that is the output, that is the package, salary package in LP. Okay, so now the point is here, both this x1 and x2 that are coming from two different Gaussian distribution, correct? So now in multivariate normal distribution, this multivariate normal distribution, and that is mu and sigma. So this mu, that will be mu x1 and mu x2. Okay, here that is a mean of this random variable x. Here this mean, this mu in multivariate normal distribution. So in this one is a mu x1 and mu x2. Okay, and this sigma. So in two dimensional, this will be not variance. Here that is a variance. Okay, but here in multivariate, this sigma, that will be covariance matrix, not variance. Covariance matrix. In one dimension, it's a variance. This one is a variance. Variance means that is how the that data points are uh, means away from the mean value. Means the data point, that the variance of a means variance of a data point uh, away from the mean value, that is a variance. So now in two dimensional or more than one dimension, this one mu, this sigma, that will be the covariance matrix. In if two input feature, the covariance matrix that will be 2 cross 2. If three input feature, the covariance matrix that will be 3 cross 3, and so on. Okay, so now covariance matrix, this one is, now you tell me the covariance matrix. So this A, B, C, D. So this A, that will be the variance of X. Okay, D. Okay, you can just sigma X square, sigma Y square, sigma X, sigma Y, and sigma X, sigma Y. So this will be my covariance matrix. So this one is the variance of X. Okay, this one is a covariance of XY, covariance of XY, and this one is a variance of Y. Okay, so in two dimensional, so next is this one is a two dimensional, let's say this one is a x, this one is a y. Okay, So this one is a, let's say this one the data point. So now this is my variance in x direction. This is the variance in y direction. Okay, and this is the variance in, not variance. So this one is a covariance. Okay, if it is positive, then it will look like this one. If it is negative, then in this direction. Clear? Okay. So in one-dimensional normal distribution, this one is a one-dimensional normal distribution. In two-dimensional normal distribution, so this will be the kind of two-dimensional normal distribution. Okay. So this one is the spread in x direction. Okay. This one is the spread in the y direction, and this one is the orientation. This one is the orientation. Clear? So variance of x and variance of y, if both are equal, then this 2D normal distribution, that will be a circle or sphere. This one. If it is positively this correlated, so like this one. If negatively correlated, then this one. Okay. So here that is a spread in x, this one is a spread in y, and this is the orientation. Okay. If suppose this covariance, that is sigma x y, that is equal to 0. Okay. So then our this normal distribution, that is parallel to this x axis, or it may be the parallel of this y axis, because one variable that does not impact on the other one if the covariance, that is x and y, that is equal to 0. Clear? So now come to this GMM in two-dimensional. So two dimension, that is x1 and x2. This one is x1 and this one is x2. So x1, let's say that is a marks in the 10th standard, and x2, that is a marks in the 12th standard. Okay. So let's say total that we have 9 observation. So now this one is my 9 kind of this observation or data point. Okay. So this data that is coming from how many number of combination of two-dimensional normal Gaussian distribution? Okay. So here the answer, that is 2. So now we will make 2 random normal Gaussian distribution. Random. Okay. So 1 and 2. Random. Anywhere we can draw this distribution. Anywhere. Any value of this mu and sigma 1, mu 2 and sigma 2. We don't know any information of this mu 1 sigma 1 and mu 2 sigma 2. Okay. So this one is a random distribution. Okay. So now we will ask to every data point that how much you have the likelihood to come in this mu 1 sigma 1, and how much that you have the likelihood to come in this distribution mu 2 sigma 2. The K means that the same question that we will ask in terms of the distance of a data point to the centroid C1 to the centroid C2, and whichever is less, the data point that belong to the closest distance of the this centroid. Okay. So now here that we will ask to each and every data point in terms of the likelihood, that in terms of the probability, that is PDF. Okay. So
this likelihood that is to come in this mu1 sigma 1 or in mu2 sigma 2. So in terms of the this probability density function. So this left side, this data set that have higher likelihood, okay, to become this mu1, to come under this mu1 sigma 1, and this right side, this data point have higher likelihood to lie under this mu2 sigma 2, isn't it? So now I repeat. So this one is my, let's say this one is a left side data point and this one is a right side data point. So now my left side data point that have higher likelihood, okay, that have higher likelihood to uh, to lie under this mu1 sigma 1, and this right side data point that have higher likelihood to come under this mu2 sigma 2. Okay, so let's say this one is, let's say for example, 75% the probability of these data point to lie under this mu1 sigma 1, and 25% probability or the likelihood to come lie under this mu2 sigma 2. The same, the 75% in this mu2 sigma 2 and 25% in this mu1 sigma 1. Okay, so this is represented by like this one. Let's say this one is my data point is this. Okay, let's say this one. So now, I'm representing like this one. The shaded region is this 3 by 4, and this blank, the reason is 1 by 4, means 75%, that is a probability of this data point, or I should say the likelihood is 3 by 4 to come lie under this mu1 sigma 1, and that is a 25%, that is a likelihood of this same data point to come under this mu2 sigma 2. Okay, so now this left side, this data point, this one be like this one, this one, this one, and this one. Okay, and the distribution that will be like this one. Okay, and here the right side point that will be like this one. Okay, so this is a left sided Gaussian distribution curve. Okay, so similarly, the right sided this Gaussian distribution curve, that will look like this one. This one, this, this one, and so this one is the right sided. Okay, now if we combine these two, this right sided and this left sided, so now this one is, so now if we combine these two like this. Okay, that is a combined effect of this left sided and right sided. So now again we will calculate the likelihood. Okay, so now what is the likelihood of the data point to be this uh, to come this mu1 and sigma 1? Okay, and what is the likelihood of a data point to be this mu2 and sigma2. Again, we have to calculate the likelihood. Okay, so now the left side data point are exactly on the center of the Gaussian distribution. Okay, then likelihood of the data point is 100% to be this mu1 sigma1, and likelihood of this right sided data point is 100% of this mu2 sigma2. They belong to this mu2 sigma2. Okay, so now if the left side and right side this data point are separated out, okay, then left side this distribution that will look like this one, and this right side that will be look like this one. Okay, and this is my data point. Clear? So now there is a again we have to rerun the same loop. Okay, means again recalculate the likelihood and then shift the distribution curve. Okay, again this recalculate the this likelihood and again that shift to the this distribution curve, and that is at the last that we will get the two cluster like this one. So there is a one important algorithm that we call as a expectation maximization. Expectation maximization. So this one is a two-step algorithm. So first step is that is expectation. Okay, and second step is that is a maximization. And this algorithm is running behind this GMM. So this expectation maximization algorithm that is also this we use in the this hidden Markov model. Okay, so this expectation, this EM algorithm, expectation maximization. Okay, so now there are three part in this expectation maximization. So first one is the initialization. So that as we had discussed the in the 1D and 2D data set, this initialization. So let us first we have, let's say this 1D data set. So now first choose the number of component, means number of component means k value. Okay, number of component means decide on the number of Gaussian distribution to use in the this model. Means the point is the data set that is composed of how many number of mixture of Gaussian distribution. Correct. So that is the first step is in initialization. First in the initialization that choose the number of component. Choose the number of component. Then second, the initialize the parameter. Okay. So initialize the parameter means that is mu1, mu2 up to this mu1, and the covariance that is sigma1, sigma2 up to this sigma n, and there is a one more parameter that we call as a weight, mixture weight. Okay, so that is pi1, pi2 and pi3 and so on, that is pi n. So mixture weight means this mu1 sigma1, that is clear. So mu1 is mean, this one that is a covariance matrix. Okay, and this pi1 pi2 this one is a mixture weight in multivariate normal distribution. So mixture weight. So mixture weight is means that is a pi1 pi2 and up to pi n, means what amount of power we should apply by the distribution to pull the data point towards to the distribution. Okay, means mixture weight is how many data point are that is coming out from the distribution. If the weight of the distribution is more, then it will pull the data point with more power. So initially that we assume that pi1 is 0.5 and that is pi2 that is again that is 0.5. Okay, because there are only two distribution, that is k is equal to that is 2. Clear? Means 0.5 0.5 means that is both the distribution that pull the data point with equal power. So there are three parameters: mu1, sigma1, pi1, mu2, sigma2, and pi2. So mu1 that is a mean, that is a covariance, and this one is a mixture weight. So initially this can be initialized random value or based on some heuristic that we will discuss. Okay, so based on the initial value we draw this two distribution. Okay, so now this step, that is initialization, that is over. Now second is that is expectation. Okay, so now second step, that is expectation. So that is expectation, second step, that is expectation, this maximization algorithm. So now in this this expectation, there is a one term that we call as a responsibility. Okay, so we calculate the responsibility. So responsibility means the formula of responsibility, that this gamma, this k into this x of I, is a one big formula, that is pi of k into probability of x of I given mu k, this variance k, sigma, that is j is equal to 1 to k pi j, probability of x of I given mu j, that is sigma of j. Okay, so where this I is the data point, and this k is a Gaussian distribution. Okay, means k that is value here 2 and I that is here, that is value 5 in case of this one dimension 1D data. So 1D data, that is I that is equal to 5, that is k is equal to 2. Okay, so now this responsibility means this one, let's say this is a 5 data point, this one 1 2 3, and this one is a 4, and this one is a 5. So how much the responsibility taken by this first distribution, towards the first data point, and how much the responsibility taken by the second distribution towards to the first data point. Okay, so for each data point, the two responsibility we need to calculate. So for total 5 data point, so total 10 responsibility value that will be there. Total 10 responsibility. So 10 responsibility means y1 this x1, y2 x1, y2 x1, y2 not y2, sorry, gamma 2 x2, this is x2, this one is x1, sorry, gamma 1. Now gamma 1 x3, gamma 2 x3, and gamma 1 x4, gamma 2 x4, gamma 5 x5, gamma 2 x5. Okay, so now the first this responsibility, so let's say gamma 1 x1, so the gamma 1 x1 that will be pi1, that is a weight, this probability, that is pdf or likelihood of this x1. Okay, given this mu1, that is sigma 1 of this first distribution, divide by pi1, this probability of this x1 mu1 sigma 1, plus pi2 probability of this x1 mu2 sigma 2. So this denominator, just you forget this denominator, because this denominator is only to normalize the this gamma, so that the numerator that remain in between 0 to 1. Okay, so where is this gamma 2 x1 is pi 2, probability of this x1 mu 2 sigma 2, and this one is same. Okay, and sum of this gamma 1 x1 and gamma 2 x1, okay, so that will be 1. So this one is, let's say, 0.75, this one, let's say, 0.25. For another data point, this may be 0.80, this may be that 0. This will be 0.20 likewise. But sum of both is equal to 1, because we have designed in such a way that sum is equal to 1. Okay, so that is a responsibility. This px1, this mu1 sigma 1, that is it is a likelihood, it's the probability density of x1 under the first Gaussian distribution. This calculated using the Gaussian probability density function. Okay, so now the second one is the maximization step. So second one is the maximization, that is the M step. So we have to find the new value of this mu and this sorry, variance and this weight, mixture weight. So now update the mean, now update the variance, and update the this weight. Clear? And it will continue till the previous value of this mu, variance, and this pi are not same as the current value of this mu, sigma, and pi. If the previous this distribution, this parameter is not equal to the current distribution parameter, then it will go on repeatedly. Now update the value of this mu, sigma, mu, variance, and pi. Again, just shift the distribution, again just relocate, and again just find new update value of this, update the value of mu, sigma, and pi, and so on. Or you run the this iteration by 10 times, let's say. Whether the convergence takes place or not, then after the 10th iteration, that it will stop. So there is another way to stop this algorithm. Or first method is, first method, if you find the this previous parameter and this current parameter value, that if both are same, then you stop the algorithm. Clear? So this one is almost the same with this k means, where this k means that is based on the this distance and centroid, and this GMM that is based on the probability and the parameter of a distribution, Gaussian distribution. Okay, so this is the basic idea of this Gaussian mixture model. It's a clustering technique. So if you have any doubt, then you please write in the chat box. So question is, why did draw these two curves? Because actually this is based on the Gaussian distribution. Okay, in the k means that we just calculate the centroid. Okay, means initial value of the centroid and just calculate the distance, and whichever the distance is less from the data point to the centroid, the data point that will come under the smaller distance of the centroid, Okay, again recalculate the centroid, then again check the distance and so on. Here in the GMM, just first you initialize one random Gaussian distribution. Okay, just find the or calculate the likelihood, and again just you shift the this distribution left hand side or right hand side. Again just you recalculate the this likelihood probability density function. So based on the this likelihood, based on this PDF, just again just you shift the this distribution curve. So once you got this exact distribution, this curve, okay, so that will be your cluster final. So the use of this one again, that is the same, that is unsupervised application, machine learning application. So in the last class that we had discussed this again, that is a customer segmentation, it's a anomaly detection. Okay, the benefit of this is uh, it is a soft clustering algorithm. It's a soft clustering technique. And the second benefit, it gives us the it provides us the extra this information of this density estimation. So as we discussed density estimation, that we will be having extra information of this mu and sigma, exact value of this Gaussian distribution, through which we can just make a new data point, and that is the reason to call it as a generative model. So okay, so if you don't have any doubt, then we wind up the session here, and let's have a 10-minute break. Then we will start the next session that will be taken by Dr. Yogesh Kumar. He is from IIT Gandhinagar. So we will start the next session at sharp 11:15. So thank you very much.